Okay, so homework 2 is due. You can drop it off here at the end of class. And homework 3 is out on the website. So you have another 2 weeks for that one. All right, so last time we talked about extended state machines, and we talked about hybrid automata. And in particular, we talked about a special case of hybrid automata called timed automata. Today, we'll revisit the questions we started last time. We talked about a whole bunch of issues that arise when you model with state machines and similar formalisms. And one of the questions was, how do you compose smaller systems to make a bigger system? And this is quite fundamental, because in any engineering design, you always start with components and you construct the design from the components, right? And so composition is a very fundamental principle in engineering, in all areas of engineering. It turns out when you're modeling with state machines, composition gets a little bit tricky. And so we're going to go through some of the issues in today's lecture. So we'll be using the same notation for extended state machines that you all are familiar with. And we'll also be using the actor model, which I believe you were introduced to at the beginning when we talked about continuous time modeling. So just to remind you, in the actor model, in the context of state machines, the actor is really modeling a system that's given by a state machine. And you just denote an actor by a box with inputs and outputs. And what we're going to do is talk about how we'll compose these different boxes together. And there's different syntactic ways of combining them. And there's different meanings that you can then give a composition. For the same syntactic way of combining two actors, you could have different meanings. Okay, so here are 3 syntactic ways in which you can combine actors. You can either combine them side by side, or you can do a cascade composition, or you can do a feedback composition. So let's look at the side-by-side composition. Okay. So there, the idea is very simple. In essence, we're combining actors in parallel. Okay. So let's say this is actor A, and this is actor B. And A might have a bunch of input ports and some output ports. And likewise, B would have input ports and output ports. And the idea with side-by-side composition is that you just combine these two and form a bigger actor from them. In a sense, you're running A and B in parallel, if you will. Okay? And now the combined actor, the inputs to the combined actor are going to be the inputs to A and the inputs to B, taken together, the union of them. And the outputs of the combined actor will be the outputs to A and the outputs to B. Okay? So this is a syntactic composition, and we'll see examples of this. So that's side-by-side composition. You can also have what's called cascade composition, which is to connect the actors in series. Okay? So the idea here is quite simple. If you have 2 actors, A and B, then A has certain input ports and output ports. And the key thing is that the outputs of A are fed in as the inputs of B. Right? So you connect them up in a cascade or in series, and then the combined actor is just going to be the combination of A and B connected in cascade. Okay? So that's the second form of composition. And for the third form of composition, we have feedback. Okay, and feedback composition, let's say you have an actor A with inputs and outputs. What you might do is take some of the outputs of A and feed them back to the input of A itself. Right? So if you have a feedback loop in your actor model, then that's a form of feedback composition. You could have other actors as well. So in this case, even in the case of the cascade, it's possible to make this a feedback model by connecting the outputs of the combined system back to the input. Okay? So feedback composition is the third form of syntactic composition. So those are all, they're just syntactic ways of combining actors, and you might have seen them before in various contexts, just with electrical circuits, for instance, combining resistors in series, or capacitors in parallel and things like that. But here we're combining state machines. In this lecture, we're talking about combining state machines. And then the issue is that the meaning of the composition is not given completely by that diagram I drew, which is just to write them in parallel. For example, like this, you have side-by-side composition, and you have an actor A and an actor B combined side by side. And the question that becomes tricky is, when do you actually execute this combined system? Okay? And there's two basic possibilities. Either you run them together, which means that the transitions or the reactions in A and B happen simultaneously. Okay? This is known as synchronous composition. Synchronous composition is used in systems that we all use every day. So what's an example of a system that's built using synchronous composition? Microprocessors, right? They're built using synchronous composition. So in microprocessors, you have one clock that's driving all parts of your chip. And that clock is synchronizing the different portions of your chip. And every module in your chip, every functional block is making transitions on, let's say, the rising edge of a clock. Okay? So you have multiple components. They're all state machines. And they're all making their transitions on the same rising edge of the clock, for example. Now, in modern microprocessors, it gets a little bit more complicated because you have multiple clock domains, and some things might be rising when you're going in the rising edge, some things might be making transition on the falling edge, and you can have divisions of the clock and so forth. But the basic idea, in the simple cases, they're all synchronized by the same clock, and so they're all making transitions essentially together. Okay, so synchronous composition is very very widely used in digital system design. Another possibility is to have the components make transitions independently. Okay? In some cases, there is no reason to synchronize two systems. Communication protocols are a great example of that, right? So in the internet protocol, this machine is talking to the iPad here, and there is no reason for their clocks to be synchronized. A message can be sent asynchronously by the laptop to the iPad, and then when the iPad receives it, it will then figure out that it has to now send the current bitmap that I just drew over to the laptop. And that can happen completely asynchronously. Okay? So another possibility to combine systems is to do it independently, and that's called asynchronous composition. Okay? Another thing I'd like to recall is the formal representation of state machines that you've all seen before. So a state machine is represented as a 5-tuple, right? A set of states, a set of input evaluations, a set of output evaluations, the update function, which is also called the transition function, and the initial state of the machine. And so now here you have a state machine A with its 5-tuple and the state machine B with its 5-tuple. And we're going to ultimately define how you combine these two 5-tuples to get this one. Okay, so that's something that we'll do in a few minutes from now. Let me first talk about synchronous and asynchronous composition. Okay, and I'll use an example for it. So here you see an example where you have two actors, and they're combined side by side. Neither of these actors has any input signal. Right? There are no input ports, but they generate outputs, A and B. So A is the output from actor A, and B is the output from actor B, and A and B are both pure signals. Okay, so let's quickly go through and understand what these actors are doing. So actor A starts in state S1, and the transition from S1 to state S2 is always enabled. right? So the guard is true. It can make this transition anytime. And when it does make the transition, there is no output associated with that, right? And then from S2, again, the transition is enabled always. The guard is true. And when it makes the transition, the output signal A is present. All right. B is very similar. It has an initial state S3 and another second state S4. And in this case, when it goes from the initial state to the next state, that transition is always enabled and the output signal is present on that one. And in the other case, the reverse transition is enabled and there's no output. Okay? So really simple toy state machines. Okay, so now let's consider what happens when we combine them synchronously. Okay? So one of the things to note here is that since the transitions are always enabled, right, they can happen anytime. There is no input to the system, so the transition can happen anytime. And we can assume in this case that there's an environment that's driving the transitions in either state machine, right? And in particular, you can think of the environment as the clock, right? The clock to both of these, and that when the clock rises, both transitions happen.
We know they can happen anytime, but does it have to?
So,
Sit there for a while and then go.
okay, good question. So the question is, let's take this state machine A. Can A stay in state S1 for some time? And the answer is yes, it could, because the way we're defining the transition is that the environment chooses when actor A is going to fire and when the transition happens. So think of the environment as making a decision. In the synchronous composition case, the environment makes the same decision for both A and B. It decides when A and B will fire together, right? But it's possible for A and B to sit in any state for some length of time. Okay, so yes, one more question?
Extending on that, could you have one of them fire and not the other one, or would that be asynchronous?
Okay, so the question is, can you have A fire and B not fire? And in the case of synchronous composition, you cannot have that. Okay, they must always, either they don't fire or they fire together. Okay, that's the semantics. And so what you get if you do synchronous composition is you get this combined actor. Okay, so let me explain how I got that. When you do any kind of composition of state machines, the set of states of the resulting machine, of the composed machine, is going to be the cross product of the states of A and the states of B. This is true for any kind of composition, synchronous or asynchronous. Okay, so the first thing we've done here is we've constructed this composed actor C, and the states of C is defined as the Cartesian product of the states of A and the states of B. And you can see that in the picture as well. What I've done is I've taken all pairs of a state from A and the state from B, right? So I have S1, S3, S1, S4, S2, S3, S2, S4, all of those states. So now the first thing you would do to construct the composition is you would actually draw these bubbles. And then after we draw the bubbles, we have to decide what's the initial state. So the way we'll define that is, in the synchronous composition case, the initial state of the combined system is going to be the one where the individual states are also the initial states of the respective components. So, so here you have S1 is the initial state of A, and S3 is the initial state of B, and that makes S1, S3 the initial state of the combined system. Okay? And then you have to decide how to draw these edges. And the way to do that is to consider what happens when simultaneously when you go from S1 to S2 and from S3 to S4, right? And so if you look at the picture here, you can always go from S1 to S2 and there's no output. And you can always go from S3 to S4 and the output is B. So the way you would combine this, you would take the AND of these two guards. You would say, in this case, true and true, which is true, right? So the combined transition is always enabled. And the set of output actions will be the union of the output actions that happen here and the output actions that happen here. In this case, there's no output associated with the transition in A, and therefore there's just a single output for the combined transition. Okay? So that's how I get this transition going from S1, S3 to S2, S4. And then the reverse transition is exactly the same. Here you have, again, the guard will be true and true, which is true. and then the combined outputs will just be A. Okay. Now we also have these two states, right? We've drawn these two states, and you can draw the transitions in exactly the same way as we did here. For example, this transition happens when you go from S2 to S2 to S1 and S3 to S4, and so the combined guard is true, and then you combine these two actions, and so you have two outputs present. Okay, but as you've probably noted by now, these two states are not reachable, right, in the state machine. It's for this system, it's really easy to look at that. You can just see the state. I mean, there's just 4 states here in the picture. You can see that 2 of the states have no edges from S1, S3, or S2, S4, and therefore you know that these 2 states are not reachable. For a really large state machine, it gets hard to do this, at least by humans, right? Even if you had an ample amount of paper, it's really hard to do this. Okay, so this becomes a problem in itself. The problem of determining if states are reachable for a combined system with many components, like a microprocessor, for example. That is called the reachability problem. The tools that we use to solve this are called reachability analysis. And this is something we'll study in April, and it's also described in a chapter later in the book, in the 3rd part of the book. Okay, were there any questions? No? Okay, so that's synchronous composition. So let's see what happens if we then combine the same 2 systems asynchronously. So now we have, again, the same 2 actors, A and B. But this time, the transitions can happen independently. So we have the same environment, but the environment is not constrained to make the 2 actors fire at the same time. So A can make a transition independent of when B makes a transition. Now, with asynchronous composition, there are a couple of different variants of how you combine the 2 actors. And the book goes through 4 such examples. What we're going to use is something called interleaving semantics. Okay? So in interleaving semantics, what happens is the environment chooses exactly one of the 2 actors to fire. Okay? The choice is up to the environment. So you can think of that as, not knowing what the environment chooses, you can think of that choice as non-deterministic. Non-deterministically, either A fires or B fires. We don't know which one. Okay? And so when we combine the 2 systems, that's the state machine we're going to get. Now, in the composition, we do the same thing as we did before. So the set of states of the combined system is, again, the Cartesian product. And so we have 4 states here. But now when we draw edges, we only have to have a transition occur in one of the 2 state machines. So again, you start in S1, S3, because that's the initial state in both cases. But from S1, S3, you can make a transition to S2, S3. So from S1, you go to S2. That transition is always enabled. But the thing is that only A fired. B did not fire. So B is still sitting in state S2. Right? So that's one possibility. The other possibility is that the environment chose B to fire first. So B made a transition from S3 to S4, and A was still in state S1. And so the label on this edge is going to be the label on the edge for B. So this transition is always enabled, and the output action is the action from B. Okay, Nima.
Why don't we have a transition from S1, S4 to S2? They both happen at the same time.
Okay, good question. So the question is, why don't we have a transition going diagonally from, say, S1, S4 to S2, S3, or from S1, S3 to S2, S4, right? So when would you have that? You would have that when both actors fire at the same time. So S1 goes to S2 in actor A, and S3 goes to S4 in actor B. This is what I was talking about as multiple versions of asynchronous composition. So what we are using is called interleaving semantics, right? Asynchronous composition with interleaving semantics. So with interleaving semantics, exactly one of the 2 actors fires. Okay? Both cannot go simultaneously. But it's also possible, there's another semantics also given in the book, which is the case where either A can fire or B can fire, or there's a third case when both A and B fire. Okay? So that version is also used in some cases. The thing to remember is all of these are modeling techniques. So if you're creating the model, you have to choose the right semantics for asynchronous composition, right? What is it you want to use? And in this case, it will depend on when the environment is going to allow the combination of actors to fire, right? And so if, for example, you were modeling a concurrent system with two tasks. Okay, the tasks can be implemented, say, as interrupts with interrupt-driven, or let's say you can think of them as threads for those of you who've programmed with threads, right? And the environment is the scheduler, which decides which task runs when. Okay. Now, if you have a single processor and you're running two concurrent tasks on the single processor, then you can't have both tasks run at the same time. Correct? So interleaving semantics is fine. Using interleaving semantics would be a reasonable modeling choice for that kind of system. On the other hand, if you had two processors with clocks synchronized, it's possible for transitions to happen simultaneously, and you might want to model that. You might want to model the effects of that. And so you could choose the alternative semantics for asynchronous composition, where either thread 1 runs or thread 2 runs or both run together. Right?
Applies in any
Okay, so the question is, does any concurrent system with preemption, is that non-deterministic, right? It depends on what you choose to model about the environment, right? So if you model the scheduler, which decides which task runs when, who gets preempted, you model all the details of the priorities between the tasks, then the system, the combined model is not going to be non-deterministic if you also include the scheduler as a third component in your model, right? Here we're not doing that. We're leaving out the scheduler, okay? And as you can see, what you end up with is a non-deterministic state machine, right? Because from any state here, from state S1, S3, you have two choices. You could go either to the state below or the state to the right. And that's because we left out information and we got non-determinism as an artifact of our modeling choice. But if I had included the scheduler, which decides which one goes when, and it has, let's say, a bit which decides whether A goes or B, factor A goes or B goes, then this would be a deterministic machine because I'd be modeling the scheduler. Okay? Other questions? Okay, so the thing to note here is that in contrast with the synchronous case, in the asynchronous case, now all states are reachable, right? And this, as we'll see in the next lecture and thereafter, that determining whether states are reachable, the technique of doing that is incredibly useful for finding whether bad thing can happen to the system, meaning you can violate an assertion, or can the system crash, or can it get into some undesirable state, or also checking if good things can happen, like what we talked about last time, or probably last week when we talked about interrupts. We had this question of, can the main program complete the while loop and end up at the location after the while loop at the end of the main function, right? That was, I think we gave it a label C. And that's a good thing. You want the main function to finish its work and then terminate, right? And so both of them are forms of reachability questions, okay? So one thing to note is the difference between syntax and semantics. When you use a modeling tool, what you will get is, if you just draw the diagram, is something like this. And so here it's the same thing, same example we saw in the previous two slides. You're combining actor A and B. You get an actor C with two output ports. But this picture does not tell you whether it's combined synchronously or asynchronously, or if it's combined asynchronously, what are the semantics, right? So you have to read the manual effectively to find out what is the semantics assigned to this sort of composition by your modeling tool, okay? And so this is something to keep in mind. Modeling tools, I mean, they could potentially include the semantics here. There's nothing that prevents them from writing that in the syntax, but your diagram gets really cluttered if you have a lot of information. So just be aware that when you're combining systems, that you know how they're being combined internally.
So when you make a model that say you have a picture like this, it matters which way the semantics are. Right?
Absolutely.
So if that's a feature of the tools, then change the
Right. Yeah, so this is the point. So the comment was that if the semantics is really inbuilt in the tool and it's not part of the modeling language, then you better understand the guts of the tool and how it exactly assigns semantics. There are some tools which make the form of composition explicit, and these modeling languages are often used in doing reachability analysis and verification. And there you explicitly say it's a textual description language, and you explicitly say whether you combine modules synchronously or asynchronously. And that helps because you know exactly the kind of composition that's being used. So in general, it's desirable to have something like this as part of the modeling language, but it's not always the case. Okay. So one important point to note is that doing asynchronous composition is not the same as doing synchronous composition, but assuming you have stuttering transitions, right? So if you go back to this picture, one might be tempted to say that what really happens here is that S1 makes a transition to S2, and S3 stutters, right? So recall that stuttering is a reaction where the state stays the same and no output is produced. But also, you can only stutter, the machine can only stutter if no other transition is enabled, right? That's also part of the definition of stuttering. So if we look at these two machines, from every state of each of these machines, transitions are always enabled, right? So from this machine over here, for A, you can always make a transition from S1, and you can always make a transition out of S2. And so you can't stutter by definition in either of these two machines. So what you get when you do a synchronous composition is something like this, and this is what we had with an asynchronous composition. And really, what's happening here is not a stuttering reaction. It's just that the way we define asynchronous composition, that there is no reaction in B, stuttering or otherwise. Okay. So all right. So now let's talk about how we would define synchronous composition mathematically. Okay. We talked about how we would do it graphically, but if you want an algorithm to do the synchronous composition for you, which is pretty much always the case because you can't do this by hand for reasonable size systems, then what you have to do is you take the 5 tuples that represent the two actors A and B, and you combine them to form the 5 tuple for the combined actor. Okay, and most of this is quite straightforward, and typically the details are really in the update function. That's where you have to be a little bit careful. So when you do a composition, synchronous composition in this case, the set of states, as we said, is the Cartesian product of the set of states of A and the set of states of B. Likewise, the input and output evaluations are also going to be the Cartesian products. Okay, so what this is representing is that the input for the combined system is going to be a pair of the input to A and the input to B, right? That makes sense. And likewise, the output of the combined system is also going to be a pair of the output generated from A and the output generated from B. Okay, that's what we have here. And the initial state is going to be, again, the pair of the initial state of A and the initial state of B. Okay, these four are pretty basic and intuitive, what we would expect. In the case of synchronous composition, the update function is not too bad. Let me just walk you through this notation. So what this is saying is, recall that the state of the combined system is going to be the so the state of the combined system is going to be a pair of the state of A and the state of B, right? And so what the update function does is it defines what SC of n plus 1 and the output of C at time n plus 1 are going to be in terms of the state at time n and the output at time n. I'm sorry, the input at time n. That should be I. Okay, so the state of the combined machine, probably have an IC here. The state of the combined machine at time n plus 1 and the output at time n plus 1 is going to be a function of the state of time n and the input, that's an I, at time n. Okay, it's just the definition of the state machine that you've seen before, right? Nothing new here. And so that's really what I have over here. It looks big and complicated, but what it's using is the state of the combined machine is the pair of the state of A and the state of B, right? That's what you have in this entire parentheses here. And this is the output of the combined machine. Y at time n. Oh, I see. So that's fine. It can be output at time n because we typically associate outputs with transitions. So that's fine. If we were talking about a Moore-like machine, then it would be output at time n plus 1. But let's avoid that for the time being. Let's go with this notation. So this is the output at time n, and that's a function. The update function is a function of the state at time n, and this is the input at time n. Okay, so and so what this is saying is that you get this update function for the combined machine by just applying the individual update functions for A and B. Okay, so the way you get SA n plus 1, the first component, and the YAN, the second component, the first tuple of the second component here, is by applying the update function for A on its state and its input. And the way you get the second part of the state, which comes from B, and the second part of the output, which comes from B, is by applying the update function for B, again on its own state and its own input. Okay, so the key thing here is when you do side-by-side synchronous composition in this way, and the actors don't share inputs and they don't share outputs, then it's really simple. You just apply the individual update functions to actor A and actor B. Okay. All right. Now, what happens when you do asynchronous composition? So here, the story is similar, except for the update function. So here, this is the phi tuple for machine M1, and that's the phi tuple for machine M2. And the combined machine is M, which is given by this phi tuple. And all of these elements, the first three elements and the fifth element, are the same as you had for synchronous composition. Okay, so they're just the cross products for these cases, and the pair of initial states here. What changes is the update function. So what happens in the update function is, and this is using interleaving semantics. So if S1 and the pair S1 S2 is your current state, and I1 I2 is the current input at time n, then we'll denote S1 prime and S2 prime to be the state at n plus 1, and O1 O2 to be the output at time n. And what happens is exactly one of the two machines makes a transition. So if machine 1 made a transition, then the first component of the combined state, which is the state of machine 1, will get updated according to its update function, and the output gets updated according to the update function. But for machine 2, the state is the same and the output is absent. Okay. So that's by definition in asynchronous composition. When you make a transition in one machine, the other machine stays in its state and generates no output. And it's symmetric for the other case. In this case, machine 2 makes a transition according to its update function, and the state of machine 1 stays the same and its output is absent. Okay? So these are the formal definitions of synchronous and asynchronous composition. This is the case with asynchronous composition with interleaving semantics. How would I change this definition if I were to use asynchronous composition with the other semantics where I allow simultaneous transitions? Yeah?
Could we just add an extra condition that S1
Okay, exactly. So you would take the definition of the case that we had in the previous slide for the synchronous composition, right, and add that as a third case here, right? So the third case would be either this or this, or S1 takes a transition according to U1, and S2 takes a transition according to U2, right? Okay. So that's all I want to say about side-by-side composition. Let's move on to the second kind of syntactic composition, which is connecting two actors in cascade. So here I have an actor A, and the output of actor A is fed to actor B, and the output of actor B is going to be the output of the combined system, and the input to actor A is the input to the combined system. All right? So let's look at an example of cascade composition. So we'll go back to the traffic light example from chapter 3, except that we're going to add a pedestrian light to the traffic light. So what we had earlier was this traffic light, where we had 4 modes of the traffic light controller corresponding to value colors of the traffic light signal. And then we had this variable count, which essentially counted time, right? So it kept track of time, and the implicit assumption was that a transition happens every 1 second. So this is a time-triggered model, and so count is really keeping track of time in seconds. All right, so now what we're going to do is add a pedestrian light. So let me just go quickly and look at the inputs and outputs here. So the input to this model is a pure signal which just tells the state machine whether or not there is a pedestrian. Okay, and the outputs are going to be pure signals which indicate whether the red light must go on, or the green light must go on, or the yellow light must go on, right? So those are the inputs and outputs. Here, what's going to happen is we will connect this input sig r, which is generated as an output by the car traffic light, to the input of the pedestrian light, okay, with the intention that when the car traffic light goes red, then the perpendicular pedestrian light can go green, right? And so you want that the red signal from the car light to be an input to this pedestrian light. Yeah.
Don't we have a feedback here? Because the signal from the light is a sig r. That comes from the traffic light, and also.
Okay, good question. So the question is, do we have a feedback here? Because seemingly, the input to the car traffic light is a pedestrian input. Okay, this is actually an input from the human, right? So from the human pressing a button, say indicating that they're waiting for the pedestrian traffic light to go green, right? This is the actual light itself, right? So so in this case, there is no feedback. Okay. Um, so the input to the pedestrian light is just the one output from the car traffic light, which indicates whether the car traffic light is turning red or not. The output from the pedestrian light is similar to the car traffic light. It indicates whether the pedestrian light is green or it's red. Okay. So the pedestrian state machine will have two states, green and red. This starts in the state green. So it starts in the state where the pedestrian light is green. You have to make sure that that is consistent with the starting state of the car traffic light. In this case, the car traffic light starting state is red, so they're both consistent. And just like we had the count signal for the car traffic light, here we have a pedestrian count signal. So it plays the same role. It's counting time. Okay. And so the implicit assumption here is again that each of these transitions happen once a second. So again, it's time triggered. In this case, the bound is less than what we have in the car traffic model. Okay, so the idea here is you initialize the count to 0 when you enter the state green, and you stay in the state green until the counter has expired. So it passes 55. When it expires, you output ped R, indicating the light is going red. You move to the state red, and then you stay there as long as the car traffic light doesn't turn red. When that turns red, you go back to the green state, reinitialize the count, and the process continues. Okay? So that's the pedestrian light model, and this is the car light model. What would be a reasonable form of composition to combine these two? Synchronous or asynchronous? Synchronous, right? Why do you say that?
Otherwise, if this one chooses not to react, they'll peak out in the actual time on the actual light, and then you might have it, and even though it's still fine.
Okay, good. So it comes from the fact that both of these are time triggered. You want them, in this case, p count is counting seconds, and so is count. And in order for them to be correctly synchronized, that is, you make a transition from green to red here in a reasonable amount of time. That car light doesn't stay red doesn't have to stay red for an inordinate amount of time. You want the transitions in both of these machines to be synchronized, following the same time signal. And so that's a good reason to have them be fed by the same clock. They maintain two counters, and they make the transitions simultaneously. Okay? Yeah. Right.
So does that mean that you have to change the initial state for one of them? Or?
Okay, so the question is that let's say the pedestrian light is green and the traffic light is red. You don't want the pedestrian light to turn red just as the traffic light is turning green. Okay, is that the question? Okay, so is that the question? It's an interesting question. So what do you think? Is that behavior allowed in this combined system? Is it possible for let me draw it out. Well, I'll draw it on the board so you have this picture also. So let's say you have a combined state where the first element of the tuple is the pedestrian light and the second is the car light. So that's how it is. And the question is, in this model, can you have a transition of this form? Mm-hmm. Okay. Okay. So in this model, the initial state, we allow the initial state green, red. It can happen when you start both machines, they would start exactly with the pedestrian light being green and the traffic light being red, right? And your concern is maybe we should allow a little bit amount of time in between just because there could be a pedestrian in the crosswalk or something, right? And you don't want the traffic light to turn green when they're there, okay? So that's a good point. This model does not take that into account, that case into account, right? How would you modify this model to take that case into account? Okay.
If you reset the red,
If you reset into the red, so the idea is you want to start with the pedestrian signal being red, let's say, and the car signal being green.
no, well, the current, the one but you should start in the red so that like
Okay.
until you get the red signal, and then you can start sending this.
Oh, I see. So you want both to start out in the red state, and then there's a timer, a short timer or something like that, which has to expire, and then let's say the pedestrian light goes green, and so you start off here in red, comma red, both lights are red, and then let's say you have another count. Let's call it just t for brevity, and then you have t is 0 when you enter the state red, red. T is incremented on every self-loop transition, and then here if t is greater than or equal to 10 or something like that, right? You make a transition to green, red, and then you start this new machine. Okay, that would be a fine design decision. Yeah. Okay, you would have to modify the rest of the state machine to do the same thing when you re-enter the state. Okay.
Could you actually like define a new state for the pedestrian light? Say like instead of going straight from green to red, go to like a blinking like red or something, and then goes completely red.
Yes, so we could certainly do that. So in the pedestrian light, we just have two possible modes, green and red, and the suggestion is let's have something which is a blinking green light or something like that, right? And that would be fine too. I mean, many pedestrian lights also have an explicit counter, right? And you can use that, incorporate that into your model as well. Okay. All right, so this is an example of cascade composition. So you take the model for the car light, and we've connected one of its outputs, which is sig r, to the input to the pedestrian light. And the output of the overall model is going to be the outputs of the pedestrian light. It's also reasonable to consider that these three can be outputs if you needed them to be. So one of the questions was that might have come up is, if you combine these two together, is it possible for you to get into a state where, let's say, both lights are green, right? So that would be a bad state, right? So if the traffic light is green and the pedestrian light is also green, well, that would be an undesirable state to have the combined machine in. Then your design is certainly buggy. So what do you think? Looking at these diagrams, is it possible that the combined system can enter the state green, comma green? Nope. So how would you reason about that? What's your name?
Chris, I mean, the only way the pedestrian machine can and the traffic light machine only produces that output when it's transitioning from state red.
Okay. All right.
It's not possible.
Okay, so that's one reason.
And the other reason is that the pedestrian light cycles out of green faster than the traffic light cycles out.
Okay, exactly. So the two reasons are, One, when in the pedestrian light signal, when you go from red to green, so when it turns green, you know that the traffic light signal in that same reaction is going to turn red. Okay, and so that's one reason. The second reason is the second question that may arise is, okay, the traffic light has gone red, but might it go green faster than the pedestrian signal? And that's where this constant becomes important. So the pedestrian signal will transition out from green in 55 seconds after it's entered that state. The traffic light signal will transition out of red only in 60 seconds, so it's longer than the pedestrian light signal. Okay, and so so we know when the traffic light goes green that it's at least been 5 seconds since the pedestrian light went red. Okay.
But isn't those two counters different counters? So maybe a lot like slower than the normal count.
Okay. Okay, good. So again, the question is, well, there are two different counters, so why should they step at the same time? And this is why we need synchronous composition, right? Because we use synchronous composition, we know that when we took this transition and set p count to 0, we also took this transition from yellow to red and we set count to 0. So when we enter the red state in the traffic light and the green state here, count equals p count equals 0, right? And thereafter, you have these the default transitions here. So count gets incremented, p count gets incremented, but they happen in lockstep. So when both of them reach 55, in the pedestrian light, you're going to make a transition from green to red. 5 seconds later, you'll make the transition from red to green in the traffic light. Okay? So it's quite hard for us, even for this really simple example. It takes a while. It takes a few minutes for us to figure out whether or not you can enter a state green, right? And it's not a very big state machine. So what is the size of the state space of the combined machine? What's the size of the state space of the individual machines? So let's look at the car light. You've seen this, right? So it's 4 times 61. What about the pedestrian light? 2 times 56, right? Now, remember that the state of the combined system is going to be, if the car is A and the pedestrian is B, the state of the combined system is going to be the cross product of the set of states of A and the set of states of B. Okay, so what does that mean for the combined system? The state space is going to be the product of these two, right? So that's certainly an upper bound on the size of the state space. So it's going to be 8 times 61 times 56, right? But we know that the state green, for example, is not reachable in this. We just reasoned that out. So the real size of the state space is less than that. Okay, so let's look at what happens if you actually draw out the synchronous composition. So if you were to do the synchronous composition as we did for the little example before, the way you do that first is you'll draw all these bubbles, and there are 8 of them. There's 2 bubbles in the pedestrian model. There's 4 in the car traffic light model. So you'll draw 8 of them. So 4 up here and 4 down there. And the initial state is going to be this is using a different combination. In this picture, the car mode comes first. So this says that the car traffic light is red and the pedestrian light is green. So it's different from what I wrote on the board. So you have 8 of these, and you draw the transitions. I'm not going to go through each transition here, but you can follow. Each transition you draw here is going to be a transition from, in this case, from red to red in the car model, and green to red in the pedestrian model. Okay, and you get a combined guard. So let's just go through this one just to make sure we've all got it. So here in the car model, you go from red to red. Okay, that's a stuttering transition, right? You're staying in the same state. You're not generating any output. but we are updating this variable. So count gets incremented. I'm sorry, that's a default transition, not a stuttering transition. The default transition, you're staying in the same state red, count gets incremented, but there is no guard associated with it. In the pedestrian light, you go from green to red, and you do that when p count exceeds 55, and the output is ped r, right? So when we combine those two together, we get this combined guard. There's a single guard which says p count greater than 55, and there is one output generated, and there is one output action which updates the state of the value of count. Okay. So the remaining transitions are computed similarly. The thing to note here is that we have some unreachable states. So up here, what you'll see is that you have this. If you think of this as a graph, you have this component in the graph, right? And there is no way to reach any of these three bubbles from either the initial state or any of these states down here, right? So the only arrows go from, in this case, yellow green to red green, or they go in between these three. Okay, so there's no way from the initial state that you can reach one of these green, green, yellow, green, pending, comma, green. Okay, they're all unreachable states. They're also the unsafe states, right? So here, if you have the state green, comma, green, well, that's clearly unsafe. Pending, comma, green, remember that pending was the state where the car light is green, but a pedestrian has walked up, and so it has to keep track of the fact that a pedestrian is waiting. And yellow green, why would that be unsafe? Cars can still go to the intersection, right? So it's reasonable to call that also an unsafe state. And in this case, we're lucky. All of these unsafe states are unreachable as well. Okay, yeah, question.
Actually, have slightly fewer state space because you can't actually have p count be like p count has to be at least 55 when it's red.
Uh-huh.
So, like for example, that isn't actually 2 times 56.
Mm-hmm.
It's more 56.
Okay, good. Right. So a good point is raised. So the question is, let's go back to the size of the state space that we wrote down here. I said this is an upper bound, right? So this size, it's really an upper bound on the state space. But we can reduce it based on what we know here. So if we go to the actual picture, the actual reachable state space looks like what we have on this slide. And so first of all, from a combination of 8 bubbles, we've gone down to 5, right? So that's lower. But also, this combination is going to be smaller because the values of p count and count increment in step, right? So if for example, you consider what happens in the red, comma, green state, then right, so suppose I'm in red, comma, green. The question is, what are the possible pairs of p count and count that you can have in this state? Well, when you enter that state, you start with 0, 0. And then as long as you're in the state red, green, the two counts are incremented in lockstep. So you go from 0, 0 to 1, 1, 2, 2, etc., down to 55, 55. And that's it, right? You're going to stop there. So if you're in the state red, comma, green, in the combined system, then the number of combinations of p count and count are going to be 56, and that's it. Okay? So counting the number of states gets harder. So you know that with this bubble, you have 56 states associated. Okay, what you have to then go down is look is for every bubble here, what are all the possible legal values, legal combinations of count and p count that you could have with each of these states. Okay, and then you add up all of those, and that would give you the total combined reachable state space of this machine.
Why do you even have the p count? Because like right now, actually you are following the count as well.
Okay.
We can actually reduce our space a lot.
Okay, Good. So the question here is, in this, if you now look at this combined state machine, it seems like there is correlation between the values of p count and count. So for example, up here in red comma green, it seems like one of these two counts is redundant. So why not just get rid of it, right? So the thing to keep in mind is that is how we actually got here, right? We got here by combining two components, which were, say, designed independently, and then they're combined, right? And one was using p count and the other was using count, okay? So when you combine two different systems, you will find redundancies there, okay? And you can optimize it based on, because you might be using the same function in two different places. Well, why do you have two copies? Why not just combine them and have a single copy that feeds both of these, right? So when you combine different systems, there are often more opportunities to optimize, okay? But still, there are good reasons to have two different components, okay? So one obvious reason is simplicity. It's easier to design a system by building small blocks and then combining them. In this case, can you think of, in this example of a pedestrian light and traffic light, can you think of another reason why you might want to have separate components? Ted? If one resets or is hacked or has a fault, that's a good reason. Oftentimes, to contain faults, it's good to have different components with their own error checking logic, so that a single fault doesn't really propagate throughout the system and mess up everything. That's a good reason. From a business point of view, also, it makes sense to have different components, right? The pedestrian light design here can be combined with other pedestrian lights in a car-free zone, right? And so you can have the same design used in multiple places. And in fact, this is how systems are built today, right? Companies, the car companies like Toyota or General Motors, they really integrate components built by a whole range of suppliers all over the world. And each supplier builds some focused component. There certainly could be redundancies amongst the different components that go into a car, but for cost reasons, you might not want to actually do that, right? Even just figuring out how you can open up and combine two components, that might be too difficult. It will mess up too many things in the rest of the system. Okay, so that's synchronous composition for connecting two systems in Cascade. Now let's look at one more example. This is an example of side-by-side composition, but this is an example where you have a shared variable. So remember in the previous examples, especially in the last one we saw, we had completely disjoint state, right? P count was the counter that belonged to the pedestrian controller, count belonged to the car traffic light controller. So the state was completely disjoint. P count could be updated independent of count and vice versa. Here we have a model of two servers. So you can think of these as serving a bunch of jobs that come in. You can think of these as, let's say, search requests that come into Google's data center. And Google has a bank of servers that can answer these search requests, right? So any request that comes in can be fed to either server A or server B. And when the server is done, it issues a done signal. Think of the done signal as the result, okay? And so you can have a done signal from A or the done signal from B. And these are identical copies. So the state machine you have up here for A is the same as the state machine you have up here for B, right? So you have a bank of identical servers. So what happens? Let's start with over here. Both of these servers share a variable called pending. Pending keeps track of the number of pending requests that have to be serviced. Okay, so since the requests are coming in to the entire bank of servers, you want to give it the incoming request to the server that's available, right? And whichever server takes up a job, if there's a certain count of pending requests, it will decrement that count as it finishes the job. Okay. So the single input is a pure signal that models the request. The output from each of these is a done signal, as I saw before. So now what happens inside each server? Well, they start in the idle state and with pending set to 0. So this is when the machines start up, the servers start up. And when it gets a request, it goes to a serving state, which models all the activities that happen when you serve that request. And then if there is no request and no jobs pending, then you are done and you go back to idle. Okay. So what happens in the serving state is, it's possible that when you're serving a request, you might get a different request. So you have to keep track of that. In this case, we're assuming all requests are identical, right? So we only have to keep track of the number of pending requests and not the details of the requests. So here we just increment the count pending and go back to serving the current request. If you get another request, you might just issue a done signal corresponding to finishing the current request. That's one possibility. Or if there are no requests, you can just stay in that state. Or if there are no requests and you have another pending job to be done, then you're going to stay in the serving state and service that pending job, which is modeled by decrementing the pending count. Okay. So there's a multitude of things you can do in the serving state. This is really, we're abstracting a lot of detail. In the real state where you're serving a request, you might have actually many more substates that model the details of what's happening inside the serving state. But for this example, I'm not concerned with that.
Aren't these models like assuming that it is not in order?
So this model. The question is, is this assuming that we're executing non-deterministically? And the answer is absolutely right. Where this model is highly simplified, and so because of that, I'm hiding a lot of detail. We have all of these transitions which are non-deterministic, right? So if a request arrives, you could either take this transition or this transition, okay? And this transition corresponds to keeping track of another pending request, and this transition corresponds to, for the same condition, finishing the current request and getting done, right? So, so this is a highly simplified model, but the point I want to make here is that you have this model that updates the count pending, and the second server, the model for the second server is also doing the same thing. It increments pending and it decrements pending depending on whether there are requests to be served or not. Okay. Now let's consider what happens when we combine these two with asynchronous composition and with interleaving semantics. Okay, so I'm taking server A and server B. I'm combining them using asynchronous composition using interleaving semantics, meaning that the environment chooses to execute one of the two actors. The other actor does not make a transition. Okay, only one of them gets to run. Okay, so in this case, is it possible for both servers to update the pending signal at the same time? No, right? Because of the definition of asynchronous composition with interleaving semantics. Only one actor gets to fire at a time, and so only one actor is going to be either decrementing pending or incrementing pending. Okay, so we can think of the updates to the pending signal as being atomic. It's not that two actors are trying to write to the signal at the same time. At a given instant, there's exactly one actor which is either reading or writing the pending signal. Okay, what about performance? So if there's a large number of requests, and you combine these two actors using asynchronous composition with interleaving semantics, then is it guaranteed that eventually we will clear all the requests? Let's say we start with 1,000 pending requests. Um, let's take the simple case first. Let's say we have 1,000 pending requests and there are no more requests coming. Will these 1,000 get cleared? Okay, so the answer seems to be yes. Why is that?
Able to take the lower black transition pending greater than 0 and not request.
Okay,
They start serving.
okay.
And then they take the second from the top. Still no request.
Okay, good. So you could even have just one server clear all those requests, right? So pending is greater than 0. This server starts, and it decrements pending, and then this server can keep taking this transition. Okay, there's no request and pending greater than 0, and it keeps decrementing pending. At some point, pending is going to hit 0. And then at that point, you go back to idle and you've served all the requests. Okay. Now let's consider the other case. You had 1,000 requests to start with, but more requests can keep coming. Depends on how fast they come. Okay. So in this model, we're not explicitly modeling time. So there is no notion of how fast they come, right? But we just assume that you can always at any point of time there is a request in the future that comes. Okay.
I just want some clarification on the request slash done.
Yeah.
What does that mean? That means like you don't have any pendings, and then we get a new.
Yeah, so it means that there is a request and we don't answer that request, but we are done with the current request that you're serving. That's why you issue the done request, the done output.
So that means we don't even increase the pending because like if there's a request coming in,
Yeah.
and we don't increase the pending, that means we're missing that request completely. If
Yeah.
you're just saying it's done.
Right.
Is that right?
I interpreted it as done with the last one, and then that server starts processing that request.
No, so what it means, right? So what it means is that you're done with the current request that you're serving. You get a new request, but you stay in the serving mode, which means effectively you're keeping track of the new request. Okay, so it's not so easy to reason about whether something will eventually happen in the future. Right, like whether all requests will be cleared if you get an infinite stream of requests. One thing you can reason about with this picture with asynchronous composition is that the environment can always choose to run the first server. So the first server might be serving all the requests, and the second server might just be sitting idle, and that's entirely possible in this picture. Okay, with asynchronous composition with interleaving semantics, because it's up to the environment to pick one of these two servers to run. Okay, so with asynchronous composition and interleaving semantics, you can get poor performance. So maybe the alternative is to use synchronous composition. So in synchronous composition, you will make sure that both of these servers always run at every step, right? So when you run server A, you also run server B. Okay, so let's say we go with synchronous composition. So what could go wrong? You can have a deadlock, okay? Okay, so so I'm not sure we have a deadlock situation here, but we do have a situation where we're incrementing pending simultaneously, right? So in particular, what could happen is you have one request, and both of these servers service that one request. Okay, so let's say both of them make a transition to serving on that single request, and when they're done, so let's say they take this transition, there's no other request, and both of them, I think okay, so we need to, let's assume we increment pending at some point. So let's say there's a second request, both of them count that second request, increment pending, and then at some point here, there's no other request, pending is 0, and they're both done, but they're both done with the same job. They both decrement pending. So even though both servers have been running, essentially serving the same job, pending is decremented twice. So there is some job which will then be ignored. It won't be served. Okay? So that's a problem.
Would be another problem if we decrement pending when we have like one pending, we decrement it twice. And look, it's checking pending is equal to 0,
Yeah.
but it's like -1.
Yeah.
And we just stay serving while we don't have anything.
Okay, good. So what could happen is let's say you're an idle in both cases. Pending is greater than 0, but maybe it's 1. And both of these make this transition. Pending is greater than 0. There is no new request. They both decrement pending. Okay, happens simultaneously. So pending gets decremented in both machines. Remember, this is a shared variable. So the decrements will happen in some order, but they happen simultaneously here. And so logically simultaneously, but they would happen in some order, and we don't know which order they happen in. Either way, it's going to end up with pending equals -1, correct? And so now we're in the situation where pending is negative, and there is no guard to deal with that except for the ones where we don't explicitly check what happens when pending goes negative or positive or 0, right? So that's another bad situation. So if you do synchronous composition of these two servers, then you have the problem of dealing with simultaneous updates to a shared variable, where the updates are really, they should be protected, right, by a lock or something like that, but here they're not. So either way, both with asynchronous and synchronous composition for these two servers, there are problems, right? But overall, which of the two would you say is a more suitable choice for composition? Asynchronous seems like a more suitable choice, right? But the problem is that you need to have more control over the scheduling of when each state machine gets to run, okay? And so we can use a variant of asynchronous composition where you have explicit control, or at least you state certain properties of the scheduler. Like the scheduler should be fair in that every server gets to run equally often on average, right, over a long run. And if you have that, then you know that you're doing some kind of load balancing between the servers, and also requests will get done more efficiently. Okay, one quick thing. So we talked about feedback composition. So in feedback composition, you have this picture where you have an actor, and the outputs of the actor are fed back as inputs. Okay. Now, with feedback composition, you have to be careful because you might get into what may seem to be circular reasoning. Okay, so no Wi-Fi. Let's see. So with feedback composition, let's say you have a system that looks like that. So sorry about that. So the output is fed back to the input. Okay, and in this case, what you might so if you look at the output as a function of the input, so O of n is a function of I of n, right? So O of n is a function of I of n. Then effectively what you have is O of n is a function of O of n, right? So you have this circular equation where the left-hand side is defined in terms of itself. It's a function of itself. Okay. So defining the semantics of feedback composition can be quite tricky. And what it needs is you need to be able to compute the solution to equations of this form. O of n equals f of O of n. Okay. Doing this involves something called fixed point computation. The solution of the equation, the O of n that satisfies this equation, is called a fixed point. You apply f to it, but it stays the same. And this is something, again, that we'll talk about in April. And so those are the three forms of composition. What we talk about next time is how to combine models hierarchically.